All right, so this week we have sections 11.2 and 11.3 to work with, and they cover area, perimeter, volume, and surface area all together. So we started off the other day working with area and perimeter. We'll do a little bit of that today, and then we'll move on to volume and surface area. The activity, I think, the hardest thing this week is probably the activity here because it involves some experimentation. And you'll either want some dot paper, which you can download from here, or if you have graph paper at home, or you can draw your own like I did in the video the other day. So I'll just show this. And it's just an array of dots like a geoboard. If you've never seen a geoboard before, they tend to be these wooden or plastic rectangles or squared with a bunch of pegs sticking up. Sometimes the pegs are nails, and you hook elastics on there to make different figures. So one thing I wanted us to do was to make some triangles. And at first I made a bunch of triangles that had an area of 3. And so my belief is that this triangle right here is going to have an area of 3. And one way we can use the geoboard to kind of play around and figure that out, aside from the formula that we talked about the other day, 1/2 base times height, we could wrap this in a rectangle and work with right triangles, because right triangles, we have a clear base and height. And these colors are too similar. So let's make this one red. All right. So either you want a piece of paper to play with to do some of these, or you want this geoboard app to kind of play with. And still, you probably have to scribble down some stuff on paper. So I am going to copy this to my whiteboard so I can scribble on it. Oh, we have another participant maybe. Add to current page. So I'm going to play with this one in a couple of different ways to review what we did last time. Hi, Kayla. And to go for perimeter also. So the kind of the basis we were going off of for area first is that the basic idea of area comes from a square or a rectangle, which is just base times height. And that this base and the height have to be perpendicular to one another. So they have to make a right or a square angle. And so we can see over here, I have right angles here and here for these yellow triangles, and then this is definitely a square. When we're working with the geoboard, our assumption is that the distance vertically between 2 points and horizontally between 2 points is 1 unit. And then we go from there. So in this picture right here, I have a square. And that square has a base of 3 units and a height of 3 units. So it has an area of 3 square units, which I'll just abbreviate like that. And what I'd like to do is from the square, think about the 3 triangles that are inside here and find the areas of each of them. So I'm making a composition from the triangle by composing a square around it. And then I'm going to decompose that square to get down to the triangle. So what I'd like to do next is to find the area of, say, this triangle up here. And it does have a pair of edges that are perpendicular. So one of these can be the base and the other can be the height. So for this first triangle, I could view this top part as the base. So it has a base of 3, and it has a height of 3. And then for right triangles, we know we can cut that in half because this triangle right here is half of the whole square, because this line right here is a diagonal of the square. So any diagonal on a rectangle cuts it in half is what we're going off of here. So that's going to be 9 over 2, and 2 goes into 9 4.5 times. So, ooh, I said 3 times 3 is 3. That's not cool. Let's fix that. 3 times 3 is 9. Oh, and let me get the chat up. I forgot about that. Chat. Okay, so if you don't have a microphone, ooh, whoa, that's not what I wanted to do. Sorry about that. I'm supposed to go up here. There we go. So either type something in the chat if you have a question, or feel free to turn on your mic and ask a question. So from the 9, I can take away that 4.5. And I also want to get rid of this triangle over here. So I have to find its area and take it away. And whatever's left has to be that one right there. So the second triangle, it has, let's say this is the base down here. So it has a base of 1 and a height of 3. So I want to take 1 times 3 and cut that in half. And often we view that as another way to write that would be 1/2 times the base times the height. Let's actually use the base of 1 here and the height of 3. But following the order of operations, oops, 3. You should give me the same answer. So half of 3 is 1.5. So from that 9, I want to take away, come on, pen, that 4.5, and I want to take away the 1.5. So 9 minus 4.5 is 4.5, because this is half of that triangle there. And then 4.5 minus 1.5 should give me 3. And so what we were developing in question 1 of the activity that we started the other day, so let's show that again here, is we're trying to develop a formula for the area of a triangle. And all of these triangles we calculated the other day, and so you'll need to show this if you haven't already. Each of these triangles turns out to have an area of 3. Other things they have in common is they all have a base of 2 at the bottom. And the distance from the baseline to the highest point, this vertex here above the base, is 3 for each of them. And so what these triangles demonstrate is that the area of a triangle seems to be 1/2 times the base times the height, regardless if it's a right triangle or not. And that is something I don't think is obvious and needs to be taught and explored. So just note on this triangle right here, we have, let's do it in green, this baseline here at the bottom. And from that baseline, we could say this is the base length. And so we have a base length on the red triangle of 2 units. Then the height has to be perpendicular to the base. That's super important up here. Otherwise, that's not the way we define area. And so from that vertex above the baseline, if I go straight down and hit the baseline with a right angle, I can see that the height of this triangle, the red one, is also 3. And so then trying out the formula, 1/2 times the base times the height, half of 2 is 1, 1 times 3 is 3, we get the same thing we get from the dissection up here. So we're verifying that the formula for a right triangle works for a triangle that's not right to find its area. Then the next problem is more of a challenge than the first one. The next one says, on a geoboard, dot paper or graph paper, make 3 different triangles that each have areas of 3.5. Now, the catch there is we have to use only the vertices of the geoboard, dot paper, or graph paper. We can't make a fractional height. And I didn't mention that the other day, but that's the point of using a geoboard. You can only work with whole number bases and heights at first. At least the horizontal and vertical distance are whole numbers. So how would we make an area of 3.5? And there are several ways to do that. Let's clear this. And I wanted you guys to play around and find them. One suggestion I gave at the end of class the other day was making a bigger grid here. And if I do that, let's say I make the following triangle here. And again, the distance between each of these points vertically and horizontally is 1. So I'm going to go down 1, 2, 3, 4, 5, 6, 7. and then I'm going to go over 1. So this is definitely a right triangle. I'm going to copy this into my whiteboard. I don't need all of it. We'll just take part of it. So we're now, based on our previous exercise, the previous part here, under the assumption that the area of a triangle is 1/2 times the base times the height, which could be also written as the base times the height over 2. Because multiplying by 1/2 and dividing by 2 are the same operation in the end, the same result. With this right here, I can see I have a base of 1 on this triangle, and the height is 1, 2, 3, 4, 5, 6, 7. So we have a height here of 7 units. So applying the formula here for the area for this triangle, we should get 1/2 times 1 times 7. 1/2 times 1 is 1/2, so I just need to know what is 1/2 of 7, and the answer is 3 1/2. So using the bigger geoboard, I was easily able to make a triangle with an area of 3 1/2 square units. So that's the easiest one to make. The other ones you have to be a little bit more clever about. And so let's bring up a different one. Pretty much the only way with a whole number base and height to end up with an area of 3 1/2 is with a right triangle, that is to have the height be 7 and the base be 1, or I could have gone the other way. I could have had, why won't that work? Interesting. Let's see, 1, 2, 3, 4, 5, 6, is that 7? 1, 2, 3, 4, 5, 6, 7. Oops, too long. So the question is this the same triangle as that one, or is it a different one? What do you think? Same or different?
Wouldn't it be the same triangle, it's just drawn in a different way?
Yeah, so in geometry, when we use the word the same, we mean congruent. And congruent means you can pick one up and sit it on top of the other and they match perfectly. Yeah, so these are the same triangle. So this wouldn't count as a different triangle that has an area of 3 1/2. It's really the same triangle. I just rotated it 90 degrees. So, so I got to be a little more clever if I want to find a, my pen stopped working on this, weird. I got to be a little more clever. So what I could do instead is just make a triangle that's not right. And there's lots of options there. So maybe I could try something like this right here. So what would this one be? We can play around and find its area. Is this too big? Is it too small? Let's wrap it in blue. And so I just kind of wanted you to play around with the geoboard, have a little exploration. So with this here, let's see, the whole rectangle has an area of 2 by 3, so it's 6. And then the question is, did I remove too much here? So here I have 2 by 1, so this triangle has an area of 1 in the upper right. In the lower right, that's 1 by 2, half of that would be 1. So from this area of 6, I just took away 1 and another 1, so that takes me down to 4. And then this triangle right here is 1 by 3. And if you take half of 1 times 3, you get 1 1/2. So let's see, that would leave 2 1/2 for this green triangle. So it's a little too small. So then I could say, well, let's try making it bigger, the whole thing. Or you could try moving the points around. What if I put one of the points over there? How big is this thing going to be? And maybe I'll scribble on it this time. Oops, new page. Let's try that again. Screenshot first. New page. what do we get here? So we're starting with 3 times 3, or 9. And then we want to remove this triangle up here, which is 2 by 3. So we want to subtract 1/2 of 2 times 3, which is going to give us a 3 to take away. And then we also want to take this one away. So that's 2 by 1. So we want to take away 1/2 of 2 by 1, which gives us 1 unit. And then this one over here, take away 1/2 of 1 by 3, which should be 1.5. So what happens there? 9 minus 3 is 6. 6 minus 1 is 5. 5 minus 1 is 4. Minus 1/2 is 3.5. Ooh, I did it. I found one. The net area here, when I take away the other stuff, is 3.5 units. So you got to kind of play around, see what you can find. It turns out there's a whole bunch, not infinitely many, but on the geoboard, there's a bunch of different triangles that have an area of 3.5, and you should be able to find at least 5, I think, where I only asked for 3 of them. And now we have 2. Okay, so getting there. Next, play around with parallelograms. So what I'd like you to do is think about this picture here. So let me bring that into a new window. Oops, it won't let me do that easily, okay. We will just zoom in. So I'm starting with this parallelogram right here, and I'm just gonna make a slice there. And then if I pick up this triangle on the left and I pick it up and move it to the other side, it should fit perfectly. So parallelograms can be easily sliced perpendicular to one of the sides, and you can pick up what you pull off and put it on the other side, and you're always gonna get a rectangle, which is kind of cool. So every parallelogram can be dissected and repasted, do a little cut and paste, and end up with a rectangle. So let's just play with another example of that. So I wanted you to make 3 different parallelograms and show how you can cut and paste to find an area as a rectangle. And then we're going to do a similar thing for trapezoids, where we can either expand by using a rectangular composition or decompose by cutting up the trapezoid internally. So let's clear some stuff here. I think I'm going to switch to the smaller board, but you could use the bigger one. Either one's fine. So I'm going to make a slightly different. So again, to use this geoboard, if you grab endpoints, you can move them around. If you need a new point, you have to grab in the middle. So kind of like it's a real rubber band. And suppose we'll make this parallelogram. All right, so there's my parallelogram right there. And I want to make a slice. So I'm going to use the green one to slice this triangle off. And then I'll make a copy of that triangle over here on this side. So I'll use green again for that. Oops. Okay, so now we have this kind of green square going on there, it turns out to be, versus the area of the red parallelogram. And so let's play and see what we got. So screenshot. And look at the whole thing. So the green square, oh, my pen is having trouble tracking. Ooh, it's not writing at all. Why is that? There we go. Maybe my computer's slowing down. The green square has a base of 3 and a height of 3. And so its area is going to be the 3 units times the 3 units, which is going to give us 9 square units, which sometimes we write as units squared. And it's the units that are squared, not the 9. There are 9 individual squares living inside that green one. Now, I'm going to next make a note about the parallelogram. The parallelogram definitely has a base of 3. It has the same base as the square. Now, the height always has to be measured perpendicular to the base line. So there's a couple ways I can view that. So if I say pick this point up here to measure the height, I have to come straight down so that I hit the baseline at a right angle. And so I can see this parallelogram has a vertical height, an altitude of 3 also. And how do these 3's relate to the area of the square? Now, again, the area of the square has to be the same as the parallelogram because I sliced off this triangle and stuck it there. So I still have the same net area, green square and triangle. So it looks like the area for a parallelogram also seems to be base times height. And the important thing we have to remember about the base and the height is that they have to be perpendicular. So what I want you to do is to create 2 more parallelograms, slice off a triangle, stick it on the other side to make a rectangle. This rectangle happens to be square, and show that either way, base times height works for both the square and the parallelogram, that they'll have the same area. So that's the goal of this next one, to verify the formula is true by using a little experimentation. Next one, we're going to do basically the same idea, but you're going to do that by making 3 trapezoids. So let's do 1 trapezoid together. And then at part 4 here is just tell me what's the general area for a triangle, general area for a parallelogram, general area for a trapezoid. And then we'll play with perimeter. So back to the geoboard. Let's get rid of some stuff here like that and this. So you could either make the same trapezoid as me or make your own. To turn this into a trapezoid, I could, for example, just move that point over here. And this is a trapezoid. A trapezoid is a quadrilateral that has at least 1 pair of parallel sides that are opposite of each other, right? Well, I guess that's parallel. So this is a parallelogram because this top edge and this bottom edge are parallel to each other. And it doesn't matter about the other 2 sides, and it doesn't matter what the interior angles are. The key is it has 4 sides and at least 1 pair of parallel sides. So with that definition, a parallelogram is also a trapezoid. But a trapezoid's a little more complicated because it doesn't have as much symmetry as a trapezoid does. So this is a trapezoid here. I could move that point over there. That's a trapezoid as long as I retain a pair of parallel sides. So that would be another trapezoid right there. But this right here would not be a trapezoid because I do not have a pair of parallel sides. So that's not a trapezoid. So I'm going to go with my original one right here. That is definitely a trapezoid. And so to find this area, I either have to compose a rectangle around it or turn it into rectangles and right triangles. And so if you look back here for this one right here, I composed a red rectangle around here, which basically adds these 2 right triangles. So we could find the area of the rectangle and then cut this upper left and upper right triangle off. Or we could make these vertical slices within the trapezoid, and then we have a right triangle, a rectangle, and a right triangle, and we would just find their areas and add them up. So you take whichever approach you want. You could do both, mix it up. But what we want to do is find the areas based on this composition or decomposition method of a few different trapezoids to see if we can come up with the area. So back to my notes. What do we got? Oh, I didn't put it in my notes yet, did I? It's over here. So I'm going to put this one in my notes so I can scribble on it and figure out what its area is. So here we're playing with, come on, pen. There we go. Area, whoa. What is going on here? All right, I'm going to try connecting a cable to my smart board, see if that helps. Right now it's Bluetooth. My electromagnetic field is interfering with Bluetooth today. All right, let's see if that works any better. Oh my, that totally messed. Okay, I think I'm all right now. All right, now it seems a little snappier and more responsive. So area of a trapezoid. And we're going to do it, I'm going to use the dissection method here. So I'm going to make a slice straight down from this top vertex down to the opposite edge here. And remember, vertices are either adjacent or opposite. They're adjacent if there's an edge connecting them, and a vertex is opposite if there is no edge connecting it. So this edge right here is not directly connected to that vertex, so that vertex is opposite this edge. And when I did that, I happened to make a right angle right there. So now I have broken this up into two figures. So I have this square here that is 3 by 3, so it has an area of 9 units squared, or 9 square units. This right here, this triangle, has a base of 1 and a height of 3, so its area is 1/2 of 1 times 3, which is 1 1/2 square units. And so my trapezoid altogether must be the sum of those. So the area of this trapezoid must be 9 plus 1 1/2. So it must have an area of 10 1/2. So we want to do this with a couple of different trapezoids. So I'll grab that other one I had, and then I'll let you do a different one, or you could do 3 of your own. So I'm going to borrow, let's say, this version here. Oops. Hang on, I have my Zoom stuff in the way. All right, so on this one right here, what do we got? So again, another area of a trapezoid. I'm going to adjust the zoom window again, sorry, there we go. So again, I'm using the dissection instead of compose first and then decompose. So I have a triangle here that's 2 by 2. So this one would be 1/2 of 2 times 2. Half of 2 is 1 times 2 gives me 2 units squared. This is a rectangle that's 1 by 2, so it should just be 1 times 2. So 2 units squared. And this is 1 by 2, so it should be 1/2 of 1 by 2, which is going to give me 1 square unit. So altogether, this trapezoid should have an area of 2 plus 2 plus 1, or an area of 5 units squared. So just based on these two examples, and you need to make a third one or make more of your own, we want to kind of figure out what's the formula here. Now, certainly you could look up a formula online, but we're hoping that our examples will help figure it out. Now, for sure, based on the idea of a rectangle, which all of our areas are based on, because we have square units, an area, a unit, is measured in terms of this square right here. That's 1 square unit, which has a base and a height. So we have to identify something that's called a base, and we have to identify something that's called a height. And these two things have to be perpendicular. So thinking about that for a minute, well, certainly this down here could be a base, couldn't it? So I have a base of 1, 2, 3, 4. And I have a height here of 2, because that red line is perpendicular. So there also seems to be a height of 2 here. But is that enough information? The answer is no, because if I go back to my geoboard here, this one has a base of 4 and a height of 3, because we have that right angle right there. But I can make the area smaller by, say, moving that point there. This trapezoid also has a base of 4 and a height of 3. And this trapezoid here also has a base of 4 and a height of 3. But I bet once we calculate it, this will have a smaller area than this one, and this one has a smaller area than that one. So what else do you think we have to take into account to find the area of a trapezoid? Any guesses? Just the bottom and the height is not enough, right? Because we can keep the same base and height by moving one of these points. So I just made 5 different trapezoids that all have the same base and height, but they definitely have different areas. What else do I need to know? The area of the triangles when dissected, yep. And so certainly when I move this top point here, I've made a different triangle on the edge. So oops, put that back the way it was. Like if I pick this up and put it there, instead of having this rectangle and triangle, if I move this point over there, then that would move this dissection, and I have a different rectangle and triangle. And I still have the same total base that they're sharing. It looks to me that the only other thing that's changed is this line up here. So just to kind of point that out, I could view either of these in a different way. So where's that geoboard? Here we go. Let's bring up another one of these geoboard apps. Zoom there. So I'm going to make a slightly different trapezoid. Oops, no, I don't want to move you. You there, and you there. And then let's compare that. Let's move this green line and put this back where it was. So here's the trapezoid I first looked at, and let's compare that one to this one. And what you should notice is that these two are congruent. I just took this thing and rotated the whole thing 180 degrees, which gives me that shape right there. So it's gonna have the same area. But now I could call this the base because it's at the bottom. However, the base doesn't have to be at the bottom, it just has to be something perpendicular to a height. So it turns out, if I'm calling this the height, this top line could be a base, and so the bottom line could be a base, and it turns out we need both of them to find this area. Okay? So I need both of those. So we'll look at it in a couple of different ways. So let's go back to the notebook. And I'm going to break this up just a little bit different. Actually, no, I'm going to do this other one, this one here. So the things I believe I need to consider here to figure out this area is that I definitely have a height, because this line is perpendicular top and bottom. So that's going to be the height. And it appears to be 3. Now I have this base down here. Maybe I'll call that base 1. It's going to be 4, but this could have been the base 2, like when I flipped it. So we're going to call that base 2. And it has a length of 3. Next thing I'm going to do here is I'm just going to do a slightly different dissection since we know a lot about triangles. What I'm going to do is break it up like that right there. So now I've broken this trapezoid into two rectangles. One has a base of 3 and a height of 3. The other has a base of 4 and a height of 3. So redoing the area of my trapezoid, oops. So trapezoid area with this dissection. So I'm just not, this isn't a right triangle, which is no big deal. It still has a vertical height of 3 from this vertex down to the opposite base. So I have this triangle up here, which is 1/2 times 3 times 3. And I have this triangle down here, which is 1/2 of 4 times 3. So if I put all that together, what am I going to get? I'm going to get 1/2 of 9, which is 4.5. And then I'm going to get 1/2 of 12, which is 6, which gives me 10.5, which I had found a very different way back here for the 10.5. If I look at this as to see like what's in common here, well, the 1/2 is obviously common to both triangles because that's part of finding a triangle. And then both of these triangles had the same height, but they had different bases. And it turns out I could kind of factor all of that stuff out because the 1/2 is the same in each of them and the second 3 is the same in each of them. So if I factor this triangle decomposition, and my claim is you can do this on any trapezoid, by just drawing a diagonal on the trapezoid. So I'm going to pull out the 1/2. So I'm pulling that out. And I'm going to pull out this times 3. So I pull that out. And what's left is 3 times 4. So what I have is this combined base going on. And so there's a couple of other ways to think about that. So let's do one more trapezoid, and then we'll go on to perimeter. New page. Let's make a different one. Let's make it taller and more skewed. Okay, so that right there is a trapezoid because I have a pair of parallel sides. So let's analyze this one. And I'm going to do it using that triangle decomposition by drawing a diagonal. Current page. So then what we're going to do is draw any diagonal you want. Doesn't really matter. Let's draw this one, but you could just as easily draw the other one. So now I have two triangles, and just a couple of things to note here. The bottom triangle, choose green, has a base of 4, and if we go from this vertex of that triangle down to the base, then we have a vertical height of 3. And then this base of 1 has this base line, and so if I measure from the vertex of that triangle opposite the base line, I get another height of, oh, I lied, that's 4, not 3. So the height of both of these triangles is what I'm claiming here. Has a height of 4 for both of them, so that's the green line. This triangle facing down has a base of 1, and this one over here has a base of 4. So breaking it into two triangles, the trapezoid area is 1/2 times the base of 1 times the height of 4, plus the other triangle, 1/2 base of 4, height of 4. And like before, we have the common 1/2, and we have the common height in each of them. So if I pull out that common height, sorry, the 1/2 and the common height, what's left is the sum of the bases, 1 plus 4. Okay, which is pretty similar to what happened last time. So this is going to give me an area, two different ways to look at it. 1/2 of 4 is 2, 2 times 5 is 10. So this red trapezoid has an area of 10 square units. Okay. Does that give you a guess at what the formula might be? And hopefully the answer is yes. So if you think about what was common here, I have two different bases because I could easily flip this whole thing. So it doesn't matter whether I look at it this way or, let's copy this to a new screen. Because if I rotate it 180 degrees, whoa, slow down. I get that trapezoid right there. It's really the same trapezoid. Now the one base is at the bottom and the four bases at the top. So we just have two different bases in a trapezoid, and those are the parallel lines. So it looks like the area formula is something like 1/2 times the height times base 1 plus base 2 is what we found in the other two examples. And so what I'd like you to do is make up a third trapezoid and test that out, make sure it works. And if you look up area of trapezoids, you'll find a formula that looks kind of like this right here. It's often written in a slightly different way. So that's one way you might see it written based on the way I factored this out. Another way is the sum of the two triangles. Often, given that we usually say base before height, it might be written as 1/2 times parentheses base 1 plus base 2, then times the height. But it doesn't matter what order we multiply in, these are equal. And instead of multiplying by 1/2, sometimes we divide by 2. So another way you might see this formula is take base 1 plus base 2 and average them, then multiply by the height. And I'll show you kind of what that looks like, that average version. We can do it right here. Let's see, I need maybe yellow to cut this up. So one way to think about averaging the bases is to kind of split the difference. So these guys line up based on this vertical line here and this vertical line here. And that slices off these triangles. So all I'm going to do is I'm just going to move that vertical line a little bit to see what happens. So if I pick up this line and slide it halfway toward this point over here, that'd be about there. I pick up this line and I slide it, oops, wrong one. Try that again. This line and move it halfway toward the opposite vertex over here. Then making these slices, I can pick up this chunk right here, cut it off, and it will fit perfectly down here. And I can cut this chunk off right here and pick it up, and it will fit perfectly down there. And so what I get is this new area, that's all of this, which is a perfect rectangle. And the base of this rectangle right here, my claim, it's the average of the two bases before. So let's just check to see if that's true. I had a base of 4 up top. I had a base of 1 at the bottom. If I add those up and divide by 2, that's going to give me 2.5. And you should be able to see here that this is 1, 2.5 when we do that slicing. So that's another way to think about the formula. So there's a bunch of ways geometrically to make sense of that trapezoid formula. All right, so you got a head start on that. Last part of this activity is perimeter. And I mentioned this is like the biggest assignment of this week. This is a lot in it. And it covers most of what's in the section, is to pick one of the figures, one of our triangles, one of our parallelograms, and one of our trapezoids and find the perimeter of them. And the catch there is we don't really have a ruler to measure it in this system here. And depending on your graph paper and dot paper, they may not work out to be nice numbers. Instead, we got to reach back to our memory from last quarter. So I'm going to use this one to find the perimeter of. And we have to whip out the Pythagorean Theorem because that's how we find lengths of diagonals. So screenshot this thing. So I'll do one of these and then you guys could do the other. So add to new page, please. And we're going to do perimeter. Try again. Perimeter with Pythagorean Theorem. And just a reminder of the Pythagorean theorem says if you have a right triangle, and right triangle means that you have some right angle, so that looks like about a right angle up at the top. So my claim is that that right there, oops, is a right angle to the best of my artistic ability. And the side opposite the right angle is always called the hypotenuse and labeled C. And these guys adjacent to the right angle are the legs. They're labeled A and B. And these are the lengths. So A, B, and C are lengths. Pythagorean theorem says that if you take each leg and measure them, and then you square those measurements and add them up, that's always going to be equal to the length of the long side. Okay. So in words, the squares of the lengths of the legs, squares of the lengths sum to the same value as the square of the long side. So in this figure over here, I just have to make a couple of right triangles to figure out the perimeter. So I can easily look at this and see that's 1, that's part of the perimeter. This is 4 down here, that's part of the perimeter, but I got to figure out what these side lengths are. So in order to do that, I have to turn that diagonal there, that diagonal line, into a right triangle. And I can do that just by drawing a line, an altitude from this vertex and an altitude from that vertex. So on this side, I've built a right triangle that measures 4 by 2. And so according to the Pythagorean theorem, to find that length, I would take my legs and square them. So 2 squared plus 4 squared has to equal this long side, I'm going to call C, has to equal C squared. So that's going to be 4 plus 16, which is 20. So C squared is 20, so C has to be whatever the square root of 20 is. Okay? And since 20 is not a perfect square, the only way to do that is to whip out a calculator. Similar on this side, we have a leg here of 4, given that's the right angle, and a leg there of 1, and this is my other C. So Pythagorean theorem says that 1 squared plus 4 squared has to equal this hypotenuse squared. So 1 plus 4, 16, whoops, sorry, is 17. That's the square of the side I want, so the side I want must be the square root of 17. So the perimeter here must be, let's switch colors. Let's see, there's that 1 at the top, plus the 4 on the bottom. And now we have a square root of 20, and we have a square root of 17. And so the best I can do to simplify this is say, well, 1 plus 4 is 5. And the only other way to finish this off is to whip out a calculator. Because without a calculator, you cannot simplify this sum any further because these two square roots are different and neither is a perfect square. So calculator time, and then we'll see how reasonable that result is. So new page, calculator. So I need to take that 5 and add it to, actually, let's just do 5 plus 1 for a sec. All right, so here's my calculator. And let's see, is the Zoom stuff in the way? There we go, that's better. So on my calculator, let's clear that. I had the 1 plus the 4, which is 5, and then I want to add on the square root of 20, close the parentheses. And so depend on your calculator whether you need to close the parentheses or not. And then I want to add on the square root of 17. And so my calculator says the total distance around should be around 1 point, if I went to 2, let's go to 1 decimal place, 13.6-ish. So this is approximately 13.6, and that's the perimeter of this trapezoid, perimeter. So just to kind of double check, this line right here is definitely, switch to my highlighter, this line right here is definitely longer than 4, because 4 is coming straight down. Here we're moving at an angle, so that's a farther distance. So that's a little bit over 4. And this line here is definitely over 4 also. So an underestimate of this perimeter would be 4 plus 4 plus 1 plus 4. So that would be 13. And it turns out that because of these lines slant, it adds on an extra 0.6. And that seems reasonable to me. So I think that is in the right range for the value. The only other way to do this is to make a ruler that has distances marked off like this right here and measure these lines out, okay, which I can't easily do on